There's a lot of hyperbole, I think, in connection with climate change. And we need to study the data, and we need to think responsibly and in a balanced way, and have a balanced and meaningful dialogue instead of a food fight, which you see on television and so on. So that's my appeal. I think it is not just a task for the engineers. I think the engineers respond to data. We need science, and we need to work together and be interdisciplinary. And, but we have to be careful we don't overreact. And we have numerous sources of projections of sea level rise, and I think we have to parse them out and decide which ones make more sense and less sense. And that's important. In many cases, I think port and coastal and transportation infrastructure can be planned for on the basis of the predictions we have now, at least reasonably so. And you'll see that my overall approach is to pose this concept of adaptive management over time. Right now, the changes in storm climatology is not that mature a science, at least as far as I can tell. And so how things change in terms of waves and wave action is less understood, and I'll give an example. A little less understood, or maybe considerably less understood than the water level changes themselves. So here I show a plot that is the just snippets from, over a 50-year span of the National Research Council methodology, which the Corps has updated in recent years. That goes back to 1987. And then also some of the Ramsdorf predictions over a 50-year period. You can obviously plot it to 100 or 200 years if you wish. I think that 50-year planning horizon is a sensible one, although we've looked at it beyond 50 years in a number of examples. If you look at it this way, you see that in 50 years, the rise in sea level from 2010 is 2 feet. If you go to the NRC2 scenario, it's only 1.3 feet. So you have to, if you wish to use those numbers, good. They're a little higher than the IPCC report that was issued last summer. As you can see here, with the bright red line, you're considerably under 0.8 meters over a 100-year horizon. I haven't noticed that any of our criteria has been updated as a result of the IPCC, and it's not clear to me why it wouldn't be. So I think we need to, consider this graph, because it's one of the most peer-reviewed of all of the projections of sea level rises. And it is on the lower side, so it deserves attention. I like this plot because it shows the overall components of sea level rise. As you can see, thermal expansion is the largest component. That is the expansion of the oceans because they're heating up. And then glaciers is the second most. The land water storage is relatively small. In business school, which I never attended, by the way, but I've read up on it, is this idea of decision tree analysis, where you try to make a rational decision as to how whether you should invest in one thing over another. So I've tried to adopt this to this case of sea level rise, and I'll step out here to do here. So if we look at the NRC, I'm going back to the NRC numbers, which are the higher of the numbers I've shown already. And we have this decision tree analysis that has each of them shown. NRC is the lowest. The medium range is the lowest at 0.2 meters over a 50-year period. And then the NRC2, I have it at 0.39 meters over a 50-year period. And then the NRC3 at 0.58. And what I've done is I've said, well, if the medium I've said that the probability is 50% that it would be on the medium path. You can change this around any way you wish. And then I've said 25% chance for each of the other two. Then you go this, I'm making a separate branch for the final 50 to 100 years. And when you do that, you then break it into different pathways. And I've gone on the NRC one thinking that if once you start on a path, you'll have a tendency to stay on that path. And then what you do is you multiply out these probabilities and the values and so on, and what I get in terms of total is that this total for this NRC1 is 0.2. It's a little hard for me to see everything here. The NRC2 is 0.55, and the NRC3 all the way down here, where am I? On this pathway is at 1. So in other words, what I'm really trying to say here is you have to basically bet all the probabilities and load them up to get this 1 meter over a century. So I've gone through it a little too quickly, but I think that if you're familiar at all with this technology, it's a very simple thing. You're just taking various things you think may happen, you weight them in terms of probability, and then figure out what the magnitudes are for each. And then you extend that. I've extended it over a 50-year period of time and then the later 50-year period of time. And these are the most likely probabilities. And again, you've got to have everything aligned to get to that one number. This now talks to changes in sea conditions and just in terms of significant wave heights around the world. This was presented at the ICE Coasts and Breakwaters Conference in 2013. And what you can see is that over here around on the east coast of Africa, you see some fairly large changes in significant wave heights. This was done by the Japanese, by the way. And up in this area, you see a little higher waves, not dramatic. You see a little more up in here. So I think it'll be some time before we have strong numbers that help us understand how the waves are changing. Of course, in shallow water, in most of the coastal engineering applications that we have, the waves are depth limited for beaches and most coastal structures. In some parts of the world where they have, like Spain, where they have large caisson structures that are in deep water, they may not be depth limited. But when they're depth limited, the waves can only be so large. But I think, I know people are working on that, but that seems quite a task to figure out what's going to happen to the waves. So this is the basic concept of adaptive management. You would start perhaps having an existing rate of sea level rise, and you might either have a new structure that you design at that rate, probably not, or an existing structure which you would have to adapt from that. And the idea is that at some critical point in time, you would make a change to your structure or your beach or whatever in order to keep pace with the sea level rise. And over 100 years, maybe you would do 1 or 2 changes. Okay, so we'll start with an example of ports. I've listed here the potential impacts to ports: increased flooding, I think we all can understand that, and related power loss that can shut things down. Weather changes that could affect shipping and cargo movement operations, bigger waves, different kinds of wave climates or what have you. Pressure on drainage systems, certainly. Increased water demands perhaps in some parts of the world. Increased temperature could have effects on buildings and how they're operated, and pavement and equipment. Potentially changes in sedimentation. And then marine structures, fendering, the structures themselves, and the issues of air draft, both under cranes and under bridges. So just to give an example of the port of, a simple example and a limited example of the port of Baltimore. This is something I learned from Dave Kriebel, a way of looking at the overall elevation changes. What you have here is you've got the storm above mean low or low water, and then for different periods in time, you have this frequency of exceedance, monthly frequency of exceedance. you see that it's creeping over time. So what some people will say is, you know, over for example, in this case, the 100-year storm is 8 feet today. In 2060, the 8-foot storm may be only a 5-year storm, meaning it'll happen a lot more frequently. But the overall change is still on the other order of 2 to 3 feet, depending on how you look at it. So we have to keep, yeah, here's the overall change, 3 feet in 70 years. So you have to keep, it's scary to think that what in the future, what today is a 100-year storm, in the future will be just a 5-year storm or so. But bear in mind how much, we're really talking about a physical change in the water itself, which here we're showing 3 feet in 30 years. If you start to look to scale for container ships, the change of a meter sea level rise, in the grand scheme of things, yeah, I guess you could reach a point where you might have to take the top layer of containers off. That would be a considerable economic impact, but ships will be changing over time as well, and who knows exactly how that will go. That's more of an economics question than an engineering question. You also have to think in all of this in the context that we're going to change the cranes, we're going to change things that wear out, we're going to change the pavement. That's part of the adaptive management. Do you repeat your designs over the next 25 to 50 years, or do you adapt and change? Here's showing one of the piers in the Port of Baltimore. You can see the 1.9 feet is over roughly a 50-year period, and we are basically, in this case, we have drainage problems, outfall. I won't go through the details of all this, but we'll have to prepare a new trench drain system to take care of the drainage. Can be managed through regrading and adding this a pumping system in this case, and it's a relatively inexpensive thing. But just to show the approach to it is, we're saying that essentially 20 years from 2010 or 25 years, you might make that investment, and then if you look at it in terms of net present value, it's essentially, if you know, it's the opportunity cost of money. If you're familiar with this economics principle of net present value, you don't spend money on something now if you don't need it now. Spend it, push it off, and spend your money on something else, and then you get this net present value in the future, and it's considerably more cost effective to take that approach. So that kind of sums up the overall thesis of, rather than going out there today and starting to raise things, we need to look at schedule planning, and the planning is a very valuable exercise. So you plan out how you might change your port or your building or what have you over time, and have a plan so that you can communicate it and people know you're doing something about it, but not spending money unnecessarily. So now let's look at Norfolk. Again, this is the same type of analysis that I showed before. You can see one of the early hurricanes here, and then essentially it's Isabel up here. You can see that we're looking at the future. These are the highest tides, and then these are the mean tides. And what you do, you can take this original mean tide and the high tides that come right out of the NOAA database, the historical database, and then you can take your scenario, extend it at the mean sea level, and then just add everything up on top, and then run your statistics again on your return periods. It's a pretty good way to look at it. At least I find it that way. So this just shows again that shift. I'm showing it from roughly today up to 2080, as we're seeing a shift in storm tides over time. And this is all with the highest sea level rise scenario. So if we look at the NIT North Wharf, you can see what happens over that time. You probably have to do something about the fendering system. You might have to do something about the loads on the berth. But you know, in the grand scheme of things, it's not that debilitating. You'd have to do a whole study, structural study of the pier and so on. But and this is the South Wharf. Here we have a little more trouble because they're already relatively vulnerable to storm tide, the 100-year tide now. And I've got other examples I'll show you in California and elsewhere as we go along. So the UK has developed a risk assessment approach for sea level rise. These categories: changes to wind, climate, and patterns, changes in precipitation, increased temperature, general climate change. And the way they've done it is they have this approach where you have the probability of it happening, and then you have the quantification of risk of it happening, where one is, give it a 1, which is green, which means no real impact, and then the yellow is an intermediate impact, and then the red, which is the 5s and 4s, is an extreme impact. So you look at these different factors. So rise, I'm just saying this is what we've done for the ports here. So rising sea and storm surge levels is the variable. It causes flooding. Its effect is potential damage and downtime and maintenance. Probability of it happening, the consequence of it happening, and we're in this total risk. The idea is that, again, this is not a situation where you do nothing. Here we would adapt over time to limit this risk and impact with fenders and drainage system changes and other things that were necessary. Then we've got something similar for, again, in this category of sea level rise, loss of, or flooding issues, loss of power, port disruption, and so on. We're going to post this somewhere, right, David? So I won't go through all of these. So you get the overall, the idea. And we have different categories, changes to wind and climate, as I said earlier. And you can go through this whole process and then come up with a final look at sea, which is ended up being this shape in the beginning. So that's just a way of looking at the risk. You can inform your clients about how to measure it overall. So this is a structural example of this is Poplar Island in the Chesapeake Bay. It's a dredge material placement site. Some of you may be familiar with it. Again, this same analysis, I won't go through it again, but this just shows the shift in return periods and water elevations over time based on the Annapolis gauge. This was the original cross-section design of this structure, and you can see it's a rock-armored revetment seawall, if you will, and it was designed for a crest elevation so that it wouldn't be over top because there's a gravel road behind it. And so basically, this I think is an important point. If you look at a coastal structure, the difference in water level over 50-year period and to a large extent over a 100-year period is not likely to make you go out and put new rock on top of this structure. The changes in rock size that are required to keep pace, at least over the 50 years, is a relatively small number. You're just increasing if you know what the SD is in the armor calculations, you're just increasing the damage that the structure will have over that 50-year time. It would be, I think, foolish to go out and overlay it with a rock that only has to be 15% higher than the rock that's already there. So I think that's the way to handle this. On the other hand, if you start to look at the overtopping, and if you're very vulnerable to overtopping, you might want to do something for overtopping. So what I'm showing here is a layer of rock and an underlayer that will provide the overtopping protection in the future. And you'll see something like that in another example later. On the other hand, when I click, this doesn't always change. Maybe it's the angle I'm at. The other thing we've been trying to work on is looking not only at using rock for such a thing, but to have grass-armored revetments. because a place like this site, which is full of sediment because it's a dredge material placement site, and they can plant grass. Of course, they'll have to mow it, which is not particularly attractive. But at any rate, there's a lot to be done. There's a lot of possibility there. And I think the softer armor, there should be more of that in coastal engineering. But it has to be pretty far out of the waves to make it effective. Just saying that if we were to do this, we might do it by 2035. Again, it's much cheaper to do it in the future. This is the cost per meter rather than to do it now. But this whole idea of grass revetments, we've been looking carefully at. There's some, so that's, I'll talk a bit more about that in a minute. Here's just showing the changes in for the coastal structure. The purple line is the change in the crest elevation that you would need over that period of time as sea level is rising. Then down here, I think importantly, is you see that the maximum SD is still only 2 in this case. So you're really not changing it very much from that water level. And I'll show you an example in California that bears the same conclusion. You look at the difference in wave height because the waves are depth limited, is hardly changing at all. So just practical things. This is a model developed by the Dutch on how to compute the forces and on grass slopes. And this gives you an idea. There are 2 failure mechanisms. One is called aggregate erosion, where you're starting to get these bare spots in here. And then there are these block erosions where you lose a big part of the revetment all at once. The structure is more resistant to block loading rather than the aggregation. But so it's all been developed on the basis of full-scale tests in Dave's favorite flume in Germany. And so what you can do with the equations that they have there is you have the wave impact forces, and it's treated as an impact force. And then you can, through a bunch of other equations, determine what the erosion depths are. And when you reach a certain erosion depth, then it's considered to be failed. This is a couple of other parameters in here, erosion parameters and number of impacts and so on. But what we found in this particular case is that the allowable wave height would be about 2.3 feet. And this is the block failure, and there's really no chance of it having block failure in this case. I'm going to keep going. All right, West Coast structure. Los Angeles, and for those of you who are familiar with California, you will already know they really don't have much storm surge. They have different kinds of waves there, much longer wave periods, but they don't have storm surge. So if you're an East Coast snob, you say they have it easy, but they say the waves are so big and they have tsunamis, that their problems are harder than ours. So this shows you the Port of Los Angeles, how its ports, this is kind of like what I showed you before, the difference with a meter of sea level rise. Not an insuperable problem. Most of these projects will be rebuilt. Few piers have more than a 50-year life. This just shows the Port of Long Beach example. Just looking at wave conditions offshore of normal conditions to look at the differences in wave overtopping that could occur in the Port of Los Angeles. This slide just shows that before and after sea level rise, you don't see a strong change in the transmission coefficient between those 2 scenarios. Well, you don't have the before. There are always gremlins. Well, that's not going to help. The point is that if I had the earlier slide, the difference between this slide and the one before it is very minor changes, because you're just not having that big a change of wave conditions relative to the wave transmission. This is the Pier 400 project, and I'm showing here, this was a landfill project for the Port of Los Angeles. And this is the most exposed face. The design wave was for the 100-year event is about a 20-foot wave. So it's a significant. It's a big wave. But it was model tested and found that it could be. They were using something like 25-ton rocks, I believe. I might have them up there. You see a need again for the change in the crest elevation, but it's relatively small because they don't have that big storm tide part of it. The change in the SD just goes from 2 to 2.4, so it's still a structure that's going to hold up. And in this case, you know, again, we might put something, some protection on the top or just on the back slope because it's slightly above the grade there. And that's what I was talking about. It's slightly above the grade. And then just looking at this a different way, because I've already showed you the numbers that are all based on Vandermeer's equations for the rock size. But we originally did a design optimization to design this structure, which balanced the damage costs, which go down the higher your return period, and your construction costs, which go up higher as you go with larger return periods. And somewhere in there is this optimal balance of damage and construction costs to get the total amortized costs. And so what happens here is I'm just showing the difference in the optimization curves with and without basically 2 feet of sea level rise over 50 years. And you see it's just not, again, it's the same thing over and over again. Okay, on to beaches. So something maybe just changing gears in a different direction. We all know, many of us know about the Bruun rule, and it's used, it's a very simple geometric method of figuring out how much beach you lose and what volume of beach you lose in a given sea level rise. And so I did an example based on the Duck Pier, and we're using basically a 90-year period or a 100-year period of sea level rise. We've got the dune heights that are close to what they have now, closure depth similar to what they have now, and all these other things. And then the retreat distance over that period of time is projected to be 53 meters, so over 150 feet, and the volume is shown here. Sorry for the metric units. And so this shows those same parameters over time. And then this shows, well, what would you do if you placed a beach fill there? They're not doing that very often there, but if you did over 10 years, this is what it would cost, and how would you go about it. And I really, you know, all in all, if you had to do this, yes, it would be expensive in a lot of ways, but if you look at the net present value of that overall, building it over, instead of doing it ahead of time, which you wouldn't do because you'd lose the sand too quickly, but if you did it overall, $1,000 a meter. So is that too much to pay to keep a beach in place over the long term with this threat? You don't have to do it now. You have to do it when the problem really faces you. So these are the kinds of questions we'd have to look at. So here, basically, I've summarized the same again, except for I've given sort of a total volume per meter per year. Where did I put that? Here. No, that's the whole 10. Oh, yeah, here it is. This 6.4. In Holland, they're putting this amount on their coast to keep pace with sea level rise, but for different reasons. Now I'm going to talk to you about work done that's an alternative to the Bruun rule, and the punchline is that it shows that the Bruun rule is at least 50% more conservative than this model. So the way you do this is you generate a 100-year storm tide series or storm time series. What we did was we just used the recorded data here at the pier and then randomized it and reused it. Then you compute the sea level rise for each storm as it occurs over time. You estimate the beach recession. We're using Dave Kriebel, and Recover, we're using Dave Kriebel and Dean model, simple model. And then we've did it in a Monte Carlo method where we're doing it over many simulations to get a good, get a better statistical assessment of the issues. And what you see, this guy Callaghan and Ranasinghe have done several studies on this, and when Marcel is here shortly, he might talk about this as well. I hope he does. So this shows the wave heights and storm surge elevations that have been recorded at the pier. This shows the significant wave heights and wave periods. And here we're showing storm duration versus wave heights. This is the idea of the recovery. I'm not going to, it's a very simple amount of, simple recovery rate that Dave Kriebel developed, and we're using that formulation. This shows the position of the shoreline over time with the Bruin rule. This is the Bruin rule numbers. This is the numbers with our simulation, which is, basically minus 20 instead of 60. I think I've got some others. This shows all the randomized storms over the time, and then this shows, which I call the banana plot. When you add in the sea level rise, you get this banana plot shape, which shows how we're going down to this 20. But we've randomized the results, whereas that first one I just showed a single curve. So I think this has a lot of promise. I'd like to see it used more. We're starting to make it part of our protocol. We've also got a separate model for the West Coast that I won't go into, but it has to be a different model because the way the beaches retreat there are different. Next subjects, sea level rise and marshes. So the idea is that as sea level rises, you want to, and these are the various factors involved, you want to understand whether a marsh will drown or keep pace. So I'm using a West Coast example. This is an environmental restoration project that we worked on. It was actually the mitigation for the Pier 400 project that I showed earlier. And we had to make this a non-navigable ocean entrance to keep it open, although we knew that it would have to be dredged, and it does. So we're just looking at this basin. I'm going to go quickly through this, but I think you'll get the basic idea. This is the marsh grass, California cordgrass, or pickleweed for different locations, elevations. This shows you the site itself. And then there's a model that's been developed at the University of South Carolina, the Morris model, and the basic idea of it is that there is a stable point somewhere that's an optimal depth where you have stable marsh, and it's going to keep pace with different changes in water level. And I'm not going to go through the equations, but we calibrated it for this case at Bataquitos. And this gives you the basic idea. You can see here that if we look at the marsh elevation, it's starting to, and this is in the NRC 3 scenario. It's beginning to take a dive here at the end of the around 80 or 90 years. Here you can see that the accretion rate is really dropping off in that period of time. So this, according to that particular model, it'll be some time before the marsh actually drowns. This is a Crone model, a separate thing. I'll just show the results for it. Crone against Morris. The Crone shows it's not quite the same thing, but you can see what is happening is the marsh started out above the water and then ends up over time being physically drowned. Whether its production is dropping off the same like the Morris model, that's not the case. But either way, it is a worrisome thing because, again, in this case, it is being submerged at that period of time. This, if you just take the vertical sediment demand for an area, this shows you how much you would need for each of the NRC scenarios. Okay, this is my believe this is my last subject. Are we doing okay in time?
Oh yeah, we're fine.
Okay. So I've been really interested in this issue of sea level rise and tidal inlets. This is a work in progress for our firm right now. We'll have it up and going, but I'll just show some results that have been developed by others. But the idea is that this is a long-term assessment of what happens to the channel itself, the ebb tide delta, and the tidal flats inside a bay and in a barrier island. And it's a fairly simple formulation. It's almost algebra. And this is what you see with the channel itself. As sea level rise, or with the increased rate of sea level rise, the equilibrium volume of the channel increases. And what you see for the same case, if you look at here's the channel volume increasing, but that comes at the expense of both the delta volume and the flat volume that are both falling off over time, quite precipitously, depending on the rates of sea level rise. So final observations, adaptive management we think is a logical strategy, and it's more economical than trying to build something today for retrofit something or build something new for the full 50 or 100 year projected sea level rise. On the other hand, if there are cases, smaller structures or whatever, where making it a little higher is not going to change the cost that much. So it has to be examined. But at the very least, I plead that people would consider this adaptive management approach. And then the cost differences between various sea level scenarios, I'm saying, are relatively small. You could see that with the rock example. You could see that with the beach example, and so on. And then planning, I think it's crucial. If you make a responsible plan, you have a story to tell to people that are ask you the question, what are you doing about climate change? So I think that's the main thing. Okay, so just for fun, I'm throwing in something which could be controversial, I suppose. But we've been looking at storm surge barriers in various locations up and down the East Coast here recently. So I'm just going to show something quickly. This author, Headland, worked out this concept that you could sort of unify the way the costs of storm surge barriers based on experience throughout the world. And these there are a few in the US shown here, but most of them are in Holland or elsewhere in Europe. And these to show more details, you can look at this at your leisure of the storm surge barriers. This is a plot of essentially the volume being the width of the structure, across the river or water body, the height of the structure, and the head, which is the water level difference. And it correlates quite nicely with the costs. This was first done in the 70s by an author named de Ritter, but it's been extended in recent years. At your leisure, you can look through all of the different gate types here, and there are pros and cons to each of them. I guess I'm sort of trying to do a public service by just getting it out there so you guys can think about it. I know it's been talked about in this area, and this will be some information you can look at your leisure and see the pros and cons of each. But that's a rising sector. Inflatable barriers, which obviously have the risk of being vandalized. Flat gate, somewhat like the storm surge barrier that Dave saw while he was in Italy.
Mosaic project
Yeah, in Venice. Sliding gates. Vertical lift gates, the problem there is if you got to get a ship under it, it's a difficult thing. I'll keep going. Radial gates, miter gate, sort of old-fashioned. This IHNC is one of the big projects of the Corps in the recent years post-Katrina, and that's their sector gates that they're using, like Port of Rotterdam. This is the sector gates in St. Petersburg. This is an Ems barrier on the Ems River in Germany. They have basically gates on the outside, and then they have two different systems, one for the smaller vessel on the. So here they've just got a gate segment, and here they have a rotary gate system, which is shown over here at the bottom. All right. This is a U.S. System done and held up quite well in Hurricane Sandy, built in the 50s after the big hurricanes that hit there. This is the Thames barrier. You probably have all seen, many of you have seen this. I think this has some, I'll go back to this in a minute, but basically you can sail right through it most of the time, and then when a storm surge occurs, you rotate this entire partial cylinder up to block the water. This is the Eastern Scheldt. I won't try to say anything in Dutch. Storm surge barrier. This cut off navigation virtually entirely. You know, a lot of people, might be controversial, but the Dutch coast is 300 miles long. It's the same length as the North Carolina coast, basically. So with their GNP and what's at stake for them, they can afford to do projects like this. I'm not sure we can do too many projects like this. So we have, in a sense, I think we have greater challenges because we have to pick and choose where the benefits are and how we go about our coastal engineering. That's not a knock on the forever innovative Dutch approach. It's just simply a fact and something that we have to bear in mind ourselves. I'm going to go through here. So, potential storm surge barriers here. I just took a shot. I don't even recall where I got this from, but just showing the areas that are potentially inundated by large storms and sea level rise. This is a VIMS report. Just for Sewell's Point, Brian Joyner, who's in the crowd here, computed this stage frequency curve, return period. So we're angling, just to play it safe, for the 1,000-year event here and what we're looking at. So Rudy Inlet, basically it's a narrow inlet, as we all know. I don't know how you would fit it in, maybe come in on the inside, but roughly 200 feet opening, 15-foot depth, using that formula I talked about before with the head and the length, and so on, $62 million. This just shows Lynnhaven Inlet, and much wider span. Now we're at 1,000 feet, 15-foot depth, $302 million. But if you look at the area that it protects, this is a lot of area that would be protected by such a structure. I'm not arguing for or against it, I'm just presenting it. It's something you would have to study in detail. Hopefully, you could provide a gate system that would be transparent to the day-to-day flow so that you wouldn't change anything or anything very much. Little Creek, just show there, a smaller 22 feet is a little deeper though, so we're here at 355 million. And then Elizabeth River, this would have a wide expanse provide a wide expanse of protection. It's the most costly one at 2.88 or 2.8 billion. The average depth across there is about 25 feet. So this is obviously a very, yes?
Can we just add in, that doesn't include pump stations, that's just stopping the water from coming in. That's
correct.
Not getting any of the water out.
That's correct.
Thanks.
Sure. Yeah, just focusing on the storm surge barrier itself. What we haven't really, taken all the way out is what would we, if anything else, would we have to do further down the system? And that's a question of phasing of where the water levels are of the hurricane between those two spots. Chances are you'd have to put something in there, but somewhere. But at any rate, I'm trying to be the provocateur here to get a discussion going on this subject. So these are the overall rough costs that include the basic information. Okay, that's it.
Okay, so well, at the end, a little provocative. Anybody have any questions?
You used probabilities. That in itself is very controversial. How did you come about those, and how did you account for the significant degree of uncertainty associated with them?
On the fault tree?
Yes.
Oh, I tried to just balance it. It's just one scenario of it, Ed. I'm intrigued by this. If you read up on this fault tree analysis in the economics books, it's at least a rational way of looking at it. And you can change the numbers any way you wish. I was trying to balance and see, at least on one of the conditions, how much would I have to stack the deck to get the 1 meter? That was my point. Everything has to go in that direction of worst case to get there. Now that's separate from, the IPCC and so on. But I think the IPCC is an important number all by itself. It's a roughly 0.8, it's less than 0.8 meters. So I think most of the dialogue in this country is not talking about the IPCC. And I can't explain why, except for that prior to, because I don't think any document has been more scrutinized or peer reviewed than that document. And I just think that so many people prior to this issuance of the report, which isn't that much different than it has been in every publication, all these other people have come up with these much bigger scenarios, and they're sticking to their guns on that. So I didn't answer your question.
Basically, it's your perception, your opinion as to what those probabilities could be.
Yeah.
And there could be 1,000 other perceptions.
Well, yeah, and that's why I just think it's a way of looking at it, and a semi-quantitative way of looking at it. And it's, you can see the examples in the textbooks where people are trying to decide whether to go into, the car repair business or the car dealership business or whatever it might be, I think it's a rational way to do it, but it's qualitative. The IPCC, like I said, I think that's a very important number.
Any other questions?
I know lots of people in the audience that are not docile, so.
Put the last picture.
Sure.
I got another question.
Oh, yes. Please do. We got.
You didn't attempt to present any kind of a surge barrier at the mouth of the bay. Is there a reason?
I didn't have enough zeros in my lexicon to.
And given in the Dutch's own acknowledgement of the environmental consequences that has resulted of these barriers, one of the questions out there is, are they appropriate for the area given what maybe the people want?
Well, to be perfect, and that's why I sort of dodged the question, but I feel that, I almost said earlier, if you look at the history of the Dutch estuaries, you see they closed off their estuaries. And the Eastern Scheldt is an example where they tried to maintain water communication. And then in Rotterdam, which is a river really more than an estuary, they're keeping the gates open most of the time. This was looked at very seriously in New York, and you will not find it in the Corps study as being on the table for, at least from Breezy Point to Sandy Hook. For those very reasons, it would change you can only have so many openings in it to make it feasible. It's already overwhelmingly expensive, and you would change the entire estuarial dynamics, saltwater wedges, it's just such a cataclysmic change that I think we have to be much more introspective about projects like that, which is not to criticize the Dutch. It's just, I just think that's the case.
I have a question.
Yeah, for existing infrastructure, you were talking about that net present value. You only spend a little bit of money every 5 years. Well, stuff that's already on the ground, I guess there's increments in.
It's more like, I'm thinking more like 25 to 50 years, but it depends.
Yeah, for some things that are already on the ground around here, you can't move
The
them up.
vast majority of what we have to protect or deal with are things built today. That's
Right.
That's another main point I try to get across is you have to think of it that way. So would you go tear something up now and rebuild it? No, you'll live with it. You might augment it. That's what I'm saying. The adaptive management is to figure out a plan as to when would you change the openings to the tunnels. If you, for example, you wouldn't change the tunnel. You would change the openings to a tunnel. And if sea level does in fact rise even 0.85 meters, there are places that, that will suffer from that. There's no question about it. The question is, when would you do it?
Right.
And how much will it cost? And then how do you do it? And what are your alternatives for doing it?
That's the whole risk analysis scenario, the colored boxes. Yeah, we use that too. Thank you.
No, I just wanted to ask your view, since you get to see what's going on all around the world. What do you think the odds are of these large structures being built in the next 50 years?
In the U.S. or anywhere?
Yeah, the U.S. Or what will make it happen?
I think it's too soon to tell, to be honest. I think that if we, even with the NRC 3, we're still at 2 feet in 50 years. How many structures do we have to change for 2 feet? I mean, whole scale change. And how many storm surge barriers do we need for that for the next 50 years? I'm just saying that I think there probably are cases where you will have to do that. I'm going to digress on one point because I think it's also important to this area. There's been we had Hurricane Sandy. Hurricane Sandy is, like your Hurricane Isabel or the 33 storm or whatever. So what have we, how does that inform what we're talking about, And there were some monumental things that went on in the New York and New Jersey area because of the storm. One of the tunnels flooded. That could have been avoided, but one of the tunnels flooded, and some of the other subway-type tunnels flooded. But when I look at the beaches, what you see, and it was really crystallized to me recently that the Corps does a good job of the ocean beach. If you go from Cape May to Massachusetts, a lot of the beach fills stayed relatively in place. The dunes were not eroded terribly. There was one breach on Fire Island, but that had been predicted long before that would happen. And in New Jersey, where the biggest storm surges were, with the exception of Manahawkin, which had no beach fill in front of it, which breached and caused an inlet. And then you saw countless times the pier with the amusement park on the top fail. But you look at that, those beaches helped prevent a lot of very heavy structural damage to the shoreline. And I think personally, I think that's a victory for the projects and for the Corps. On the flip side, and I think it really comes to light now, when you look at the inland, the back bay shorelines, they're not protected at all. So most of the big shutdowns, the reason people can't go back to work and they may lose their houses altogether are because of the backside barrier. And if you look at urbanized beaches, and Norfolk is largely and Virginia Beach, an urbanized beach, the idea of festooning flood walls now so that for this very infrequent storm, is probably financially and socially unacceptable. So we live with a system wherein the Corps does their part, and then the backside is all covered by FEMA. So we have this hybrid system of two government agencies that really don't connect all the way. I know they connect, and I'm not criticizing, I'm saying it's a fact. And that busts our continuity, in my mind, of our ability to protect to a level that people can really understand and can be communicated. And so you see people, I think this is a big issue, and I think some countries, some parts of this country better communicate risks than us. I wonder if you took a poll of people that lived in back bays in New Jersey, how many of them thought that the Corps' project was supposed to protect their home? Probably most of them. And I'm not criticizing the Corps or anybody or FEMA or anybody. I'm just saying risk communication is something we have to work on. Sorry, that's almost an editorial.
No, well, I think that added a lot of value to what this large audience came here for, is to hear you're from New York City.
Sort of. I'm really from Key West, Florida, but that's a different Navy brat.
This is a very interesting one. As you said, in a couple of places there are some references that if we wanted to dig deeper, you're going to provide those references to us.
Yes.
Right? The reason I mention it is, for example, if you can show the slide on the Elizabeth River and your barrier, that one. I don't know if...
Well, I deliberately left out the option that only closes off your river, Dave.
No, I know. That's
I thought that would be impolitic.
I want to hold this up. This would be the last point. Just to show how academia can get involved. I'm responsible for the Senior Civil Engineering Design Project this semester. And we have a team that's looking at a movable floodgate barrier across here. And these young senior civil engineers are very having a difficult time coming up with the cost. So your little curve there with the estimated cost is really going to help them. Now, are there any of those students in the room? I told them that if they didn't come to this lecture, they would fail the course.
They don't get and they don't get the paper.
They don't get the paper, but I'll make sure they get the paper. So, thank you, John.
Thank you.